Introduction to TCP Fast Open. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to take a deep dive into TCP Fast Open, commonly abbreviated as TFO. This is a TCP extension that was designed to eliminate the latency penalty associated with the traditional TCP three-way handshake for repeat connections. If you have ever wondered why subsequent requests to the same server can be faster than the initial connection, TFO is one of the technologies that makes this possible. TCP Fast Open was standardized in RFC 7413 back in December 2014. Building upon experimental work that began at Google around 2011. The core innovation is allowing application data to be sent along with the initial SYN packet, rather than waiting for the handshake to complete. This seemingly simple change has profound implications for web performance, reducing latency by one full round-trip time for established client-server relationships. The technology works by introducing a cryptographic cookie mechanism. When a client first connects to a server, the server generates a unique cookie and sends it back to the client. On subsequent connections, the client can include this cookie along with application data in the very first SYN packet. The server validates the cookie and, if valid, processes the data immediately without waiting for the handshake to complete. Let me walk you through the diagram that illustrates the evolution of TCP performance optimizations. We start with traditional TCP, which represents the original TCP implementation that requires a complete three-way handshake before any data transmission can occur. This traditional approach connects to TCP Fast Open, which represents our main topic and the technology that reduces connection latency by allowing data in the SYN packet. TCP Fast Open then connects to the TFO cookie, which is the cryptographic token that enables the server to validate returning clients. This cookie mechanism is crucial because it provides the security foundation that allows servers to trust and process data from the initial SYN packet. The TFO cookie connects to reduced latency, which represents the ultimate benefit of eliminating one round-trip time from the connection establishment process. The reduced latency component connects to faster web, representing the practical outcome of these optimizations on real-world web performance. Finally, faster web connects to better user experience, which is the end goal of all these technical improvements. Every millisecond saved in connection establishment translates directly to improved user satisfaction, especially for users on high-latency connections like mobile networks or intercontinental links. TCP Fast Open Solution Overview. TCP Fast Open elegantly solves the handshake latency problem by allowing data to be transmitted in the very first SYN packet, but only for clients that have previously connected to the server. This approach balances performance optimization with security considerations, ensuring that the benefits of faster connections do not come at the cost of increased vulnerability to attacks. The solution introduces a two-phase approach to connection establishment. During the first connection to a new server, the client performs a standard three-way handshake but requests a TFO cookie from the server. The server generates this cookie using a cryptographic function and sends it back to the client. On subsequent connections, the client can include both the cookie and application data in its initial SYN packet, and the server will validate the cookie and process the data immediately. This design preserves backward compatibility with existing TCP implementations. If either the client or server does not support TFO, the connection simply falls back to the traditional handshake with no negative consequences. This graceful degradation has been crucial for the gradual adoption of TFO across the Internet. Let me explain the flowchart that illustrates the TFO decision process. The flow begins at the start node, which represents the moment a client application initiates a TCP connection to a server. From start, we move to the first decision point, has cookie, which asks whether the client already possesses a valid TFO cookie for this particular server. If the answer is no, meaning this is either the first connection or the previous cookie has expired, the flow proceeds to normal handshake. This node represents the standard three-way handshake process. After completing the normal handshake, the flow moves to request cookie, where the client includes a TFO option in its connection indicating it would like to receive a cookie for future use. The server receives this request and the flow moves to server generates cookie. At this node, the server uses its secret key and a cryptographic function to generate a unique cookie for this client. The cookie typically incorporates the client's IP address and a timestamp to ensure it cannot be reused by other clients or after expiration. From server generates cookie, the flow moves to store cookie, where the client receives and stores the cookie for future use. The client must persist this cookie, typically in memory or a connection cache, so it can be included in subsequent connection attempts to this server. Now let us trace the alternative path. If the client does have a cookie, the answer to has cookie is yes, and the flow proceeds to send SYN with data and cookie. This is the key innovation of TFO: instead of sending a bare SYN packet, the client includes both the stored cookie and the application data it wishes to send, all in a single packet. The server receives this combined packet and the flow moves to server validates cookie. The server recalculates what the cookie should be for this client using its secret key, and compares it against the received cookie. This validation ensures that only legitimate returning clients can benefit from TFO. If validation succeeds, the flow proceeds to accept data early, where the server processes the application data immediately, before the handshake completes. The server can even begin sending response data back to the client. This early processing is where TFO achieves its latency savings. TFO cookie generation and security. The TFO cookie is the cornerstone of the entire TCP Fast Open security model. Without a robust cookie mechanism, TFO would be vulnerable to amplification attacks and other forms of abuse. Understanding how cookies are generated and validated is essential for both implementing TFO correctly and appreciating its security properties. The server generates TFO cookies using a keyed cryptographic function, typically an HMAC or similar construct. The inputs to this function include the client's IP address, a timestamp or time window identifier, and a secret key known only to the server. By incorporating the client's IP address, the server ensures that cookies cannot be transferred between different clients. The timestamp component allows cookies to expire, limiting the window of opportunity if a cookie is somehow compromised. The secret key used for cookie generation must be protected carefully. If an attacker obtains this key, they could forge cookies for any IP address, completely bypassing the security that TFO cookies are meant to provide. Servers typically rotate this secret key periodically, which automatically invalidates all existing cookies and forces clients to obtain new ones through the standard handshake process. Let me walk you through the sequence diagram showing the cookie generation and usage process. We have three participants: the client representing the application requesting a connection, the server representing the destination system, and the crypto module representing the cryptographic subsystem within the server that handles cookie generation and validation. The sequence begins with the initial connection phase. The client sends a SYN with TFO request to the server. This is a standard SYN packet that includes a TCP option indicating the client supports TFO and would like to receive a cookie. The TFO option is defined in RFC 7413 and uses option kind 34. The server receives this request and initiates cookie generation by sending generate cookie with client IP to the crypto module. The server passes the client's source IP address as input to the cryptographic function. This IP binding is crucial for security. The crypto module performs the cryptographic computation and returns the cookie value to the server. This cookie is typically 4 to 16 bytes in length, depending on the implementation. Longer cookies provide more security but consume more space in the TCP options field, which has limited capacity. The server then sends a SYN ACK with cookie to the client. This response completes the standard handshake acknowledgement while also delivering the newly generated cookie. The client stores this cookie for future use. After the client sends its final ACK and data, the normal connection proceeds. But the important part comes on subsequent connections. When the client wants to connect again, it sends a SYN with cookie and data to the server. This single packet contains the initial handshake request, the previously received cookie, and the application data the client wants to send. The server receives this packet and sends validate cookie with client IP to the crypto module. The server provides both the received cookie and the current client's IP address for validation. The crypto module recalculates what the cookie should be for this IP address using the current secret key. The crypto module returns the validation result to the server. If the calculated cookie matches the received cookie, validation succeeds. If they do not match, perhaps because the cookie was for a different IP or the server's secret key has been rotated, validation fails. Finally, assuming validation succeeds, the server sends a SYN ACK and processes the data immediately, demonstrating the latency savings of TFO. The server can begin processing the client's request and even start sending response data before the handshake fully completes. Complete TFO connection flow. Now let us examine a complete TFO connection from start to finish, including both the initial cookie acquisition and the subsequent optimized connection. Seeing the full flow helps illustrate exactly where the latency savings occur and how the two connection types differ. In a typical scenario, a web browser connects to a server for the first time. During this initial connection, it performs a standard handshake but also requests and receives a TFO cookie. The browser caches this cookie, typically for several minutes to several hours depending on implementation. When the user clicks another link or the browser needs to make another request to the same server, it can use the cached cookie to skip the handshake latency. The latency savings may seem small in absolute terms, often just tens of milliseconds for nearby servers, but they compound across many requests and become significant for distant servers or mobile users. Studies have shown that TFO can reduce page load times by 10 to 15% for typical web applications, with even greater improvements for users on high-latency connections. Let me walk through the detailed sequence diagram showing both connection phases. The participants are the browser, representing a web browser or any client application, and the web server, representing the destination that will serve content. The first section shows the initial connection. The browser sends a SYN with TFO option to the web server. This SYN packet includes TCP option 34, which indicates TFO support and requests a cookie. The option contains a zero-length cookie field, signaling that the client does not yet have a cookie and is requesting one. The web server responds with SYN ACK with TFO cookie. The server includes the generated cookie in the TCP options of its response. The cookie is cryptographically derived from the client's IP address and the server's secret key. The browser stores this cookie for future connections to this server. The browser sends ACK to complete the handshake. At this point, the TCP connection is established through the standard three-way process. The browser then sends get/index.html as its first request. Note that this request could not be sent until after the handshake completed, which is the latency penalty we are trying to eliminate. The web server processes the request and sends the HTTP response containing the requested content. The browser receives this response and renders the page. Later, when the user navigates to another page on the same site, the second connection begins. For the subsequent connection, the browser sends SYN with cookie and get/page2.html. This single packet contains everything needed: the handshake initiation, the authentication credential in the form of the cookie, and the actual application request. The browser does not wait for a handshake response before sending this data. The web server validates the cookie and, finding it valid, immediately processes the HTTP request. It responds with SYN ACK with HTTP response. Notice how the server's handshake acknowledgement includes the beginning of the HTTP response. The server can start sending content immediately without waiting for the client's final ACK. The browser sends a CK completing handshake while simultaneously receiving response data. From the browser's perspective, it sent a request and started receiving a response in roughly 1 round-trip time, compared to 2 round-trip times for the initial connection. This 1-RTT saving is the core benefit of TCP Fast Open. Configuring TFO on Linux. Linux has supported TCP Fast Open since kernel version 3.7, released in December 2012. The implementation has matured significantly over the years, and modern Linux distributions typically include TFO support enabled by default for clients. However, server-side TFO often requires explicit configuration, and understanding the various options is essential for optimal deployment. The primary control for TFO is the sysctl parameter net.ipv4.tcp_fast open. Despite the IPv4 in the name, this parameter controls TFO for both IPv4 and IPv6 connections. The value is a bitmask that allows independent control over client and server TFO functionality, with options for unconditional operation or operation only when cookies are valid. Let me explain each line of the configuration code block. The first command checks the current setting. The command sysctl net.ipv4.tcp_fast open reads the current value of the TFO control parameter. The sysctl utility is used to read and modify kernel parameters at runtime. The net.ipv4.tcp_fast open parameter is the specific kernel tunable that controls TCP fast open behavior. When you run this command, it displays the current value, which determines whether TFO is enabled and in what mode. The second line shows example output. net.ipv4.tcp_fast open equal operator 1. This output indicates that TFO is currently configured with value 1, which means only client-side TFO is enabled. The server will not accept TFO connections from other clients with this setting. The next section explains the possible values. A value of 0 means TFO is completely disabled for both client and server roles. This is the safest setting if you are concerned about potential security implications or compatibility issues. A value of 1 enables TFO for outgoing connections only, allowing this system to use TFO when connecting to TFO-enabled servers but not accept incoming TFO connections. A value of 2 enables TFO for incoming connections only, making this system a TFO server that accepts TFO connections but does not use TFO when initiating outgoing connections. A value of 3 enables TFO for both client and server roles, which is the most common setting for systems that both initiate and accept connections. The next command enables full TFO support. The command sudo sysctl-w net.ipv4.tcp_fast open equal operator 3 modifies the kernel parameter at runtime. The sudo prefix runs the command with root privileges, which is required to modify kernel parameters. The -w flag indicates a write operation. The net.ipv4.tcp_fast open equal operator 3 sets the parameter to enable both client and server TFO. This change takes effect immediately but is not persistent across reboots. To make the setting persistent, you need to add it to the system configuration. The command echo net.ipv4.tcp_fast open equal operator 3 feet pipe sudo tia/etc/sysctl.configuration appends the setting to the sysctl configuration file. The echo command outputs the configuration line. The pipe sends this output to T, which writes to the specified file. The flag appends rather than overwriting. The /etc/sysctl.configuration file is read during system startup, so this ensures the setting persists across reboots. The final command sudo sysctlp reloads all sysctl settings from the configuration files. The P flag tells sysctl to load settings from /etc/sysctl.configuration and any files in /etc/sysctl.d/. This confirms that your persistent configuration is valid and applies it immediately. Benefits, limitations, and best practices. TCP Fast Open offers compelling benefits but also has limitations that must be understood for effective deployment. The technology is not a universal solution and works best in specific scenarios. Understanding when to use TFO and when other optimizations might be more appropriate is key to maximizing network performance. The primary benefit of TFO is reduced latency for repeat connections. For mobile users or users connecting to geographically distant servers, saving one round-trip time can make a noticeable difference in perceived performance. Web applications with many small requests benefit most, as the connection overhead represents a larger fraction of total request time for small transfers. However, TFO has several limitations. It only helps for repeat connections to the same server. The first connection still requires a full handshake to obtain a cookie. It requires support on both client and server sides, which limits its effectiveness on the public internet where not all servers support TFO. Additionally, some middleboxes like firewalls and proxies may interfere with TFO by stripping TCP options or blocking packets that combine SYN with data. Let me explain the comparison table that summarizes when TFO provides the most value. The table has 3 columns: scenario, TFO benefit, and recommendation. The first row covers high latency connections. In scenarios where the round-trip time is already high, such as intercontinental connections or satellite links, the TFO benefit is marked as excellent. The recommendation is strongly enabled, because saving 1/RTT when RTT is already 200 or more milliseconds represents a significant percentage improvement in connection time. The second row covers mobile networks. Mobile connections often have high and variable latency due to radio interface delays. The TFO benefit is very high because mobile users experience the latency most acutely. The recommendation is enable with monitoring, because while the benefits are substantial, mobile network middleboxes sometimes interfere with TFO. The third row addresses short-lived connections. For connections that are established, used briefly, and then closed, such as typical HTTP requests, the TFO benefit is high. The recommendation is enable, since the connection overhead represents a large fraction of total time for short-lived connections. The fourth row covers long-lived connections. For connections that stay open for extended periods, like WebSocket connections or database connections, the TFO benefit is low. The recommendation is optional, because the one-time handshake overhead is amortized over many transactions, making TFO's savings relatively insignificant. The fifth row addresses first-time visitors. For users connecting to a server for the first time, TFO provides no benefit because there is no cached cookie. The recommendation is prepare cookie for future, meaning the server should still send a cookie during the initial handshake to benefit subsequent connections. Now let me walk through the best practices diagram. We start at the TFO deployment node, which represents the decision to implement TCP Fast Open in your infrastructure. From here, 4 main branches extend to different consideration areas. The first branch goes to enable both sides, emphasizing that TFO requires both client and server support. From enable both sides, an arrow leads to test middlebox compatibility, highlighting the importance of verifying that network equipment between clients and servers does not interfere with TFO packets. The second branch goes to monitor cookie hit rate. This metric indicates what percentage of connections are successfully using TFO versus falling back to normal handshakes. A low hit rate might indicate cookies are expiring too quickly or middlebox interference. From monitor cookie hit rate, the flow continues to tune cookie lifetime, where administrators adjust how long cookies remain valid based on observed usage patterns. The third branch goes to implement rate limiting, which is essential for preventing abuse. From implement rate limiting, the flow proceeds to set per IP limits, establishing bounds on how many TFO connections can be initiated from a single source IP address within a time window. The fourth branch goes to plan for fallback, recognizing that TFO will not always succeed. From plan for fallback, the flow moves to graceful degradation, ensuring applications handle TFO failures smoothly without visible impact on users. From graceful degradation, we reach log TFO failures, which is important for identifying patterns in TFO problems and optimizing deployment. All these considerations feed into improved performance and reliability of your TFO deployment. The key takeaway is that TFO is powerful but requires thoughtful implementation and ongoing monitoring to achieve its full potential. Thank you for your attendance. Please consider subscribing to the channel and liking this video.